Welcome back to Lecture 6. Lecture 6 is going to be on templates. This will be a short lecture as promised at the beginning of the last one. The idea of templates are sort of the bread and butter of the data structure part of the course. The idea will be that templates will enable us to write a very generic structure. In Java, you might remember the int list class where you wrote an integer-based linked list. And if you wanted to have that same linked list instead hold characters or floats, you'd have to rewrite all that code to have a char list class or a float list class. The idea with C++ will be that a template enables us to simply write a class that holds something, and then we can fill in that something later on. So as a sort of motivational example, let's consider the integer swap function. So the return type of this would be void. We've got the name, which is swap. We will pass in two references, an int reference x and an int reference y. And of course, that was something we couldn't do in Java. If we want to do swap two integers, what we would need to do would be to have the two integers stored inside a class or an array. If you were to pass two integers in just as parameters, they would automatically be passed as passed by value in Java. So here we can pass by reference and could actually just send two integers in to be swapped. And so the way the old code works then is you have the idea then of a temporary variable int temp, and then you would say temp equals x, and x equals y, and y equals temp. And now we've managed to switch the values inside x and y. So that's your swap code. And certainly this is a reasonable function to have. The sort of problem we run into is that if I wanted to write a similar function for char or float or chord or any other type I want to swap two of, the code would be nearly exactly the same. And we'd have the standard create a temp, write one of the values into temp, write the second into the first, write your temp back into the second. Even the reference variable declarations would be the same. The only thing that would change would be the fact that we'd be passing in two strings or two chords or two floats rather than two ints. And then, of course, the fact that whenever we passed in chords or strings or floats, then that type would be the type of our temporary local variable as well. So when we deal then with the idea of templates, the idea is to treat the type as a variable itself. In other words, what we will do up here is the first line we will add to this is going to be template class eType. So you have the word template, and then inside the angle brackets, the less than and greater than symbols, you write the phrase class eType. And in place of eType, we could have the capital T or GOBJ for generic object, or basically any other name you want. But that eType there is just some variable name that will stand in for a regular type name. And then that variable is used when you have these types. Instead of int here, here, and here, we will have eType here, here, and here. So that now is our template swap function. The only thing we've changed was that we filled in this imaginary type called eType in place of the three ints, and then we put this line at the top of the function so that it was clear eType wasn't something we just made up out of the blue. We have this template declaration line to indicate this will be a template with generic type name eType. And by saying class eType, we're implying eType is the name of some class, whether chord or string, or if you want to view the built-in types as classes, the class int or float or char or anything. So this is the eType or T or GOBJ or myType or whatever you're going to use as your type variable name is then the name of some class. And now then that is what's filled in those places. So what we are doing here now is essentially parameterizing type. Making the type a parameter that we can change at will. Now this is beneficial to us because now when we want to go ahead and make certain calls, all we are going to do here now is say, well, somewhere here in main, I have an int I and a j, and we initialize them for some whatever. And then I want to swap these two. I just go ahead and call swap I and j. And the system now tries to find a function called swap that takes two integers as variables, and it doesn't find one, but it does find this swap function that takes two e-types as variables, and it says, hey, if e-type was integer, or type int, then this would work. So it says, let's produce then a version of the swap code where int is filled in for e-type. And so the code you wrote as a template then is copied by the compiler. Int is filled in for e-type, and basically an integer swap code is generated, and this then calls that integer swap code, and that is how your code is compiled. So the idea is then this template is just used by the compiler to produce the integer version or whatever other version you want. The same thing would be the case if in the same code even we said chord C1, C2, and tried swapping C1 and C2. So this doesn't need to be in separate code. I'm not restricted to just using the template using one kind of type. I can use many kinds of types in my template. So now the idea is I'm calling the same swap code, but this time around I've got two chords I'm passing in, and so now the compiler says, well, I've still got this swap that takes two e-types. If they were both chords, then that would match this. So let's go ahead and make a new copy of this swap code, replacing e-type with chord. So now we'll have the original template version, and a version that has the e-type replaced with int, and a version that has the e-type replaced with chord. And the compiler is generating these for us. But the idea then is that then that chord-based code is what is used then for this particular function call. And so all the template simply enables us to parameterize the type so that when I call swap with two integers, we fill in the integer for the e-type. When I call it with two chords, we fill in chord for the e-type. The one thing that would not be allowed would be this. If I want to swap C1 and I, because those are two different types, and we only have one e-type, both of the parameters in that swap code, and both of those parameters in that swap code were both e-type. They have to be the same type. Just as if you say x plus x, you can't magically have x be two different values inside that expression. It's the same value in both cases. Likewise here, this variable that holds a type name has to hold the same type name in both areas in that line. So this is the same type repeated twice. You can't have different types. Therefore, this line would not be allowed because it's a chord and an int. It doesn't match the signature that says pass two of the same thing. But that would be your function. That would be your function usage here. That's the example of the usage. This is the example of the .h, or that the .c file would have this. The .h file would have just this part, where you'd have your template line, the swap method signature with the semicolon, and so you'd have this top part in a .h, and then everything minus the semicolon in a .c. And that would be how you'd deal with your templates. Now, more interesting for us would be the usage of these templates inside a class. So let's go back to our chord class. Let's go back to our second version where I had here. Among other things, private data. I had a double X chord and Y chord. And I had a string pointer called my name. And then there's a closing of our class. And let's imagine we had said, well, I don't necessarily want my, whatever the label of this is, to be a string. Maybe I want to label it with an integer, or maybe I want to label it with a color, or whatever else. So let's parameterize this to have a generic label type. We'll have a coordinate, an x coordinate and a y coordinate, and then some generic label type that we'll decide on later on. So again, we write the template line at the top, templates inside angle brackets, class e-type. And then in place of string, instead of a string pointer, we could have an e-type pointer. And just as in lecture 5, instead of a string pointer, we could have just had a string member data. We used a pointer specifically to illustrate the big three. Likewise, instead of an E-type pointer called my name, I certainly could have had just an E-type variable, E-type my name. That would have been okay as well. I'm just saying since we had a string pointer before, let's have an E-type pointer now. So I'm just trying to be consistent with the code we wrote last time. But the idea now would be all that code we wrote last time, the ideas would be the same. It just instead of string, we would have some generic E-type. And we'll talk about the implementation in a second. This would be the chord class now. And just as with the swap function, your template line up here extended from the opening brace to the closing brace of the swap function. Likewise, the definition of E-type extends from the opening to the closing brace of the class. And therefore, it's clear then what this E-type is supposed to be doing. So I can go ahead and make other declarations here without a problem. Here I have public, and I can say, for example, my no argument constructor, or I can say the, let's say we have here a chord reference, assignment operator, chord reference. I'm going to call it X instead of a rig val just because I'm running out of room for the variable name. So we looked at that last time, but we have there a chord reference, that's a return type, and the parameter would be chord reference X. We saw that before. Those would be two possible declarations, and notice there's nothing special there indicating it's a template. There's no reason to have it in there until you hit the semicolon at the end of the class. Once you leave the class declaration, this template bit loses its effect. You'll then, on every implementation function, need to rewrite it. And in addition, the type from now on will be chord with something inside the angle brackets. So the idea here is that within here, it's just chord, and we're using chord wherever. But as soon as we hit the semicolon and we're out of the class declaration, then the type is not going to be chord. Chord, whenever used as a type, will always be followed with an open and close angle brackets and something written into that slot. And the question is what? Well, the first thing we can worry about is how to actually declare variables using this class. So let's consider now the, what we can say here is we can have the idea of chord. Again, we need to fill something in there. This will be the variable C1. In this case, our label pointer will be an integer pointer. And in the second case, we'll have what we had in the last lecture, which is that it's a string pointer. So that would be an example of how to actually declare variables using this template. We have the type chord, but instead of just saying chord C1, we say chord with the open and close angle brackets and the actual type we're filling in for the E-type here. So when we were just calling a function, the arguments we are sending to this function naturally indicated which types to match to the parameters. Now we don't have anything special like that. You don't naturally pass arguments to an object except for the constructors, and we didn't parameterize anything in the constructors. So the idea here now is you actually physically write the type that gets filled in for E-type within these angle brackets. So this is a chord of type template type int, variable name C1. Or the type is the chord with template type string, C2 is the variable name. And so in the first example, we will take all the original code and we'll make a copy of it with int substituted for E-type. In the second example, we'll take all this original code, make a copy of it with string substituted for E-type. So once again, this template is used by the compiler to generate the specific versions of the classes that we need in order to run create our variables. But we don't have to write all those different versions. We just write the template and let the compiler do the rest given those results. Now, as far as actually defining the functions, this is where things get interesting, because now if I want to, for example, define the operator equal, the assignment operator, well, I need a template line because we needed a template line above our class, our .h, our class declaration. And now, just as with swap, every time we're going to be using E-type inside our function, we need to make this a template function. It's a template implementation function for one of the member functions of our template class. So we need that line above, and then we will say, once again, that chord, when used as a type, needs to be followed by angle brackets. So before we even have the ampersand for the indicating it's a chord reference, it's not a chord reference, it's a chord E-type reference. This is your type. Chord with angle brackets following it with something written in there. And since at this point we're still writing the definition rather than allocating variables, we don't know specifically what E-type is going to be, so we continue to use the generic type. Here, we use the generic type and scoping the function name to the class name and then the parameter itself would be a chord E-type reference X. So the return type has angle brackets after it. The class name itself has angle brackets after it, and the parameter type has angle brackets after it. In all three of those situations, chord is being used as a type. And so there is no longer any such thing as a chord type. It's chord with angle brackets and a type filled in those angle brackets. Here, the type is generic because we're just defining the function, but we're not choosing specifically what value gets written in there yet. And then on that previous slide where we had the declarations, we are choosing specifically to put int or string in there and finish off the template by giving the E-type a real value to store. And so then we would have the code here for here. The slight difference with the constructor would be that here, if I say, again, I need a class E-type inside angle brackets above each function, so the definition for the constructor would need one of those as well. I, again, as it did up here, scope the function name to chord with E-type and angle brackets after it. But the function name or the constructor chord is a function name. So there is no E-type after that. That is, we happen to name constructors for the class that they are a part of. So in this case, the constructor is called chord. Making the class a template doesn't affect that, and this is not a type. This is a return type. This is a class, so it's a type. This is a parameter type. This is a function name. So the function names won't change. Therefore, your constructors are still called chord, and your destructor is still tilde chord. It is the class name and the parameter and return types that are going to have this angle brackets after them. But the constructor name doesn't, the function name itself doesn't change. And so there's an example of how it doesn't change. That's really all there is to say about templates. They may seem complicated at first, but unlike maybe some other things we've talked about, they actually are pretty easy once you've seen them a few times. So templates are just one of those things that are on the surface intimidating, but I think we've already discussed things like returning by constant reference and other such things that are harder to understand conceptually than templates. Templates are just a matter of seeing more examples. So don't be too alarmed. In section 2, you're going to see an example of this. You look at the array class in detail, and the array class is going to be a template class where we hold, instead of an array of ints or an array of chars, we hold an array of whatever, and you will see the extensive class. You'll see many uses of this template syntax, both the template class declaration and a template function for each implemented member function, and you'll see all sorts of ways in which this E-type comes into play. And so that, at that point, should hopefully clarify things. There's not a whole lot of rules to worry about. All you need to remember is that you have, outside of the class declaration itself, chord followed by E-type and angle brackets, or chord followed by some real type and angle brackets. And if you can keep that straight, that whenever you want to use chord as a type, it's chord followed by something in angle brackets, you should be okay as far as class templates go. But you will see plenty of examples of that syntax, and so you shouldn't let it worry you too much. You'll have plenty of chance to let your mind get adjusted to this idea before you have to deal with code itself. Any questions? Or I guess you're not here, no questions. It's been a long evening. I guess that's it then, folks. That's the end of Lecture 6. And the Lecture 7 that we will discuss, we'll have up shortly, we'll be dealing with inheritance. That's the topic for 7. It might bleed a little bit into Lecture 8. And then after that, a quick bit on abstract data types, and we will then start talking about data structures, most notably linked lists. So we're done now for templates. Like I said, don't be too alarmed if this seems a little confusing. It's really not anywhere near as confusing as it seems at first glance, unlike some other things that are perhaps more confusing than they are seeming at first glance. That's it. I will see you in Lecture 7. Take care.